Let us look at proposition number 18 of book 10 of Euclid's Elements. The proposition says, if there are two unequal straight lines and to the greater there is applied a parallelogram equal to the fourth part of the square on the less, but falling short by a square, and if it divides it into incommensurable parts, then the square on the greater is greater than the square on the less by the square on a straight line incommensurable with the greater. And if the square on the greater is greater than the square on the less by the square on a straight line incommensurable with the greater, and if there is applied to the greater a parallelogram equal to the fourth part of the square on the less but falling short by a square, then it divides it into incommensurable parts. It's a big proposition, but basically it is very similar to the previous propositions. There we were talking of commensurability. Here we are talking of incommensurability. So that's the only difference. So let's see how we can prove this. We are given two unequal straight lines A and BC, where BC is greater than A, and we apply a parallelogram BD by DC with a square remainder. And how to apply this parallelogram we saw in the lemma of the previous proposition. Now this parallelogram should be such that BD by DC is equal to fourth part of the square on A. Let BD be incommensurable in length with CD. So we have BC square is greater than A square by a square on a straight line incommensurable with BC. Now we bisect BC at E and we take a point F such that EF is equal to ED. We know how to do that, right? Draw a circle with the center at E and radius as ED and take the opposite intersection to D. So EF is equal to ED. Now if EF is equal to ED and E is a midpoint, that means BF is equal to CD. So which means BC is cut into two parts, two unequal parts. And more appropriately, BC is cut into equal parts at E and into unequal parts at D. Now we had a proposition in book 2 which said that if that is the case, then BD times DC plus ED square is equal to EC square. Now we quadruple each of these quantities. So it becomes 4 times BD by DC plus 4 times ED square, which is equal to 4 times EC square. Now BD by DC is this rectangle 4 times, and this rectangle is 1/4 of A square. So if we take 4 times of this, that means it is equal to A square, and ED square would be 1/4 of FD square. So if we take 4 times ED square, it means FD square, and EC square is 1/4 of BC square. So 4 times EC square will be BC square. So this becomes A square plus DF square is equal to BC square. Or in other words, BC square is greater than A square by DF square. We started off by saying BD be incommensurable in length with CD. So BD is incommensurable in length with CD. Now, if BD is incommensurable with CD, that means BC, which is the sum of BD and DC, BC is also incommensurable in length with CD. And CD is commensurable with CD and BF because CD will measure itself. And CD is equal to BF. So CD is commensurable with CD and BF. So BC is incommensurable with CD, CD is commensurable with CD and BF. That means BC is incommensurable with CD and BF. But CD and BF are parts of BC. That means BC is incommensurable with the remainder FD. So we have BC square is greater than A square by A square on a straight line which is incommensurable with BC. So that was the first part of the proposition. Now let's look at the second part, which is basically the opposite of converse of this. So we start with this, we have to end up with this. So we start off by saying BC square is greater than A square by A square on a straight line incommensurable with BC. And we follow the same procedure. We apply a parallelogram BD by DC with a square remainder. And finally, we end up with BC square is greater than A square by DF square. We know BC square is greater than A square by A square on a straight line incommensurable with BC. Now, BC is incommensurable with DF. So, BC is incommensurable with BF plus BC. So, BC is incommensurable with DF. That means BC will also be incommensurable with the remainder BF plus BC. But BF plus BC is commensurable with DC. The sum is commensurable with a part. If the part is commensurable with the other part. And we know they are commensurable with each other because BF equal to C. So here BC is incommensurable with BF plus DC. But BF plus DC is commensurable with DC. That means BC is incommensurable with DC. Taken separately, we say BD is incommensurable with DC, which is what we had to show. So that is proposition number 18 of book 10 of Euclid's Elements. Again, let me remind you, there is a link to a PDF book which describes all these propositions in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now.